And then we see the data. Totally, we have 55 runs, different experiments from a test rig. And so for here, I only present one example of the raw data of the pump speed. And the x-axis is the transient sequence time. As you see, the raw data has really large spike values and also have very large noise. The first thing we do is the data reprocessing. We do the downsampling to 10 Hertz, and we have eliminate many noise and spike values. And after this data preprocessing, now I present all the 55 runs data. The first is the gate opening, and the second is pump speed. As I mentioned before, all the gate opening, they have the same gradient. So you see the slope is the same. But actually, we have experimented with various different pump speeds to capture a broad range of the pattern. We want to have a different shape of the pump speed settings, so we have more thinning data. Okay, so indeed, so these two different gate opening and pump speed, they have result in significant different height. Yeah, we have different shapes of height, and our work based on those data points. Okay, so this is the data. Next is for the height prediction models in the solutions, the HM. We use a really simple artificial neural networks actually to make this height prediction model. And also we treat the data as independent, which means we have established the quasi-static models, but actually we have established two models. The first model have two input features, pump speed and the gate opening. We denote the model as a F1 model. Actually, we have the second model. Except the pump speed and also the gate opening, we also include the gradient of these two parameters. dnp dt, the gradient of the pump speed, d alpha dt, the gradient of the gate opening. We denote these models as F2 models. So far, we have established two models. Then we should training the model and check the model's prediction capabilities. So in next slides, we have training the models on 55 runs, since we totally have 55 different experiments. So we have leave one out, the whole unseen experiments for validation. And this is for the validation case 1. And also we have compared these two models' prediction capabilities, and then we see the results. First, we focus on the left-hand side figures, and the figure represents the height, and the black color represents the measurement, experiment measurements, and the F1 model is in the blue curve, and F2 model is in the red curve, and the x-axis is the time. As you see, the F1 and F2 model, both of them can capture the trend of this height change during this transient sequence. But actually, both of them are failed to predict the height gradual return to the stable state in this at 20 seconds. So we should find the reason, and we focus on this time period, and we see in these figures, the blue color is the gate opening, and the brown color is the pump speed. As you see in this period, the gate opening and the pump speed, they remain constant. But why this height will has a gradually change to the stabilized conditions? The reason is that this happens just after the termination of the gate one change, and the whole system, this closed loop system is really sensitive. They need some time to go to stable and from a saturation with the accelerating flow. But this phenomenon cannot capture by the quasi-static model. Okay, but actually, these two models can capture the trend. And then we see the second examples for case 2. Still, these two models can capture the top and the peak of this height in the transient sequence, but then also fail to predict the height recoveries. still just happens after termination of the kind of open change. The system needs some time to go to stable. Okay, so this is the disadvantage of this quasi-static model, but actually these two models can capture the trend, the peak, the highest peak quite well. So we combine F2 models, the second models with PID control for the case 1 to see if we can optimize the pump speed in the transition sequence to decrease height fluctuations. And now we see the result. Still, we focus on the left-hand side part. This is the figure represent the height during this test. So the black color is the measurement height, is the original height. And the red one is our F2 model combined with PID strategy optimized height. And the right part is another figure to represent to show this pump speed, and the red color is our optimized pump speed. As we see, after optimization, the height has a really has a much smaller fluctuation compared to the measurement. As you see, when the height go really low and our strategy has increased a lot of the pump speed, help this height to go back to the desired height at around 7 meters. And when the height increased too much and our strategy has controlled pump speed to slow down and to help the height to remain constant. Okay, but the one disadvantage of this strategy is that we cannot skip the first fluctuations of the height. The reason is that the closed loop system is really sensitive, so we should control the pump speed before the kind of open change. So we cannot control the pump speed after we know after this kind of change start to adjust. So, but this is the limitation of the PID control. We cannot use the features to control the time for now. So yes, so in next stage we should use a more advanced control system to make this pump speed to adjust before the relevant open change. Yeah. And for the conclusion, outlooks. First, we have combined this artificial neural network and the PID controller, and they have shown the capability to decrease height fluctuations during this transition sequence. But still, we found that this quasi-static algorithm cannot capture the pressure recovery, the gradual return of the height. But next, we should do more experiments with different round blade angle, guide opening, and height to enhance the model and controller. And finally, as I mentioned before, the quasi-static model cannot capture the time sequence in the data, cannot capture the pressure recovery, the gradual return of the height. So we should more advanced algorithm, time series method, deep learning methods to predict the height, and also combine with the model predict control. Use the futures guide open changes value to control the pump speed at this time, at the current time. But of course, we have since this presentation is, but since this is a pilot project we finished last year, and we also have done more work about these studies. I can show one examples. We have applied LSTM. This is new models, deep learning models, to our data. As you see, these two examples is much better than the quasi-static model by simple neural network. We can capture the trend, but also we can capture the time sequence. We can capture time lag in the pressure recovery and also the height recovery. And this model will combine with the MPC, and we can control pump speed before the change of the guide open, and we can eliminate even the first peak of the height. Okay, thanks for the SVC to funding this project, and thank you for Wharton for providing so valuable data sets. And thanks for listening, and I'm volume to discuss, and with regards with the machine learning and every details in these studies. And also welcome to questions. Thank you.
Thank you, Xiao, for your very interesting presentation. And as I said earlier, we will answer all questions at the end of the webinar. Feel free to write any questions in the chat in the meanwhile. We have a question right now, but I think that we will wait until the end of the webinar. But thank you for your interest. Now on to artificial neural network, which Andrea from Luleå's Technical University will talk about. And you are very welcome to start your presentation whenever you are ready. And we can see your PowerPoint now. And your laser pointer.
Thanks, Andrea. Good day, everyone. My name is Andrea Toffolo, and I'm giving this presentation on behalf of the team that carried out this project at Luleå University of Technology, led by Professor Michel Cervantes. I'm also professor in energy engineering at another division from Michel. My division is the one of energy science. So the title of the presentation, which is the same title of the project, is Turbine Power Characteristic Prediction with Artificial Neural Network. In this presentation, I will give you first a brief introduction to the project. Then I will show you some of project results. And then I will discuss the importance of modeling the turbine performance with artificial neural networks. And I will show you how these results can be exploited with a very ultimate goal that I will keep until the very end of the presentation. So the goal of this project was to develop a database model to reproduce the characteristic curves of a turbine. And the purpose was to specifically investigate what are the ingredients that are necessary to set up this kind of model. So the parameters that are necessary and sufficient, the number of measurements that are needed to be fed to the neural network, the network structure, in order to reproduce the characteristic curves of a turbine. Well, what are neural networks? Maybe not all of you know what they are. Well, artificial neural networks are a very versatile computational tool, and they are considered to be universal approximators. They work as our brain cells, a network of our brain cells. So let's say in our brain, the cells receive signals from other cells. The signals are bioelectric or biochemical signals, and they elaborate them and return another signal that is transmitted to other cells. The computational neuron does exactly the same. It receives numerical signals from the other artificial neurons. These signals are weighted and all summed up, also with a bias, to be the input to an activation function. And the result of the activation function is the output of the computational neuron. So each neuron performs very simple and computationally fast mathematical operation. In the network, these neurons are organized in layers so that the input of one layer, the output of one layer becomes the input to the next layer. And in order to reproduce the relationship between a set of input data and the corresponding outputs, these inputs and outputs are fed to a training algorithm that adjusts all the weights in the neurons and the biases, so that the error is minimized between the input data and the corresponding output, predicted output by the neural network. So our intention was to investigate how many layers does this network have to, then how many neurons per layer, which are the most suitable activation function, and how large is the set of the experimental data needed to for training such networks. The training data we used were experimental data from the downscale model of the Porteous U9 turbine, which is a Kaplan turbine. And in this presentation, I will show you the results obtained for the turbine efficiency as a function of the guide vane angle, the head, and the blade angle. You see here in the figure an example of, for one blade angle beta, the grid of experimental data as a function of the head and the guide vane angle. So we had available measurements for 10 blade angles, and for each blade angle, we had more or less 20 to 25 guide vane angles and 7 heads. First, I would like to show you some preliminary results that we made at the beginning, some tests of neural networks with just 2 inputs that were the guide vane angle and the head. So tests that were run for one blade angle at a time, giving, of course, one neural network at a time. And as you see from the figures here on the right side of the slide, you see that the surfaces we obtained were very smooth and regular, just with a simple feed-forward network made of one hidden layer with 4 neurons. So we had 2 inputs at the beginning, the guide vane angle and the head. We had 4 neurons with an activation function, which is the tan sigmoid function. And then we had one output layer with a linear function. Of course, we needed this tan sigmoid function to give some curvature to the surface. Otherwise, if you use only linear function, you just get linear outputs that are linear in the input. So they're not good to represent the efficiency curve. With these networks, the standard deviations of the predicted efficiency from the experimental efficiency was as low as 0.16 efficiency points, so a very good result. But then we wanted, of course, to generalize this relationship as a function of the blade angle also. So we went for a network with 3 inputs, guide vane angles, head, and blade angle. And as you see from the figures here on the right, we got to plot a generalized surface for any blade angle. And so we got this envelope of all the surface of turbine efficiency for different blade angles, which is the actual surface that gives the best turbine efficiency for any condition of guide vane angle and head, which is the surface onto which the turbine should operate with always the best efficiency for any condition. And this set of surfaces was predicted with a simple feed-forward network with 1 hidden layer and 6 neurons only. So these results can be obtained with very, very simple networks. Of course, the complexity of the network is always a trade-off between overfitting and underfitting. So if you use a low number of neurons, you get a very smooth surface that doesn't interpolate the points, while if you use many neurons, you probably go after some irregularities in the measurement uncertainty, and then you overfit your surface. And in this case, the standard deviation was 0.36 efficiency points. So given the larger number of data to be interpolated, clearly also the standard deviation goes up a bit. But why is it important to try to model the performance of turbines with neural networks? Well, that's because principle-based modeling for complex flows needs excessive computational resources and time. So, you know, if you want to reproduce the performance with CFD, for example, we need a very large computational time. And so there is the need to move towards a data-driven based modeling with machine learning. In particular, neural networks models are suitable to reproduce this relationship governing the operation of hydraulic turbines and can be used in real-time applications. And this is a very important feature because it suggests the way in which these results can be exploited. And in particular, we went for a type of diagnostic applications because neural networks reproduce, of course, the relationship among turbine operation quantities when the turbine is not affected by performance degradations or faults. So let's say in a healthy status. And then if we have available this prediction of how the performance of the turbine should be in a healthy state, we can compare what we measure in real time from our data acquisition system, compare with the predictions of the real networks, and of course, if something is different, then we can use these differences to detect performance degradations or faults. But if we do this at the overall system level, so looking at the overall turbine, well, it's very difficult to distinguish which performance degradations or faults are active. We just see that something is wrong, but we don't actually see the origin of this malfunction. So the fingerprints of these different performance degradation or faults are very confusing and may be confused at an overall system level. It is much more convenient to decompose the system into different control volumes or subsystems and investigate the relationship among the quantities within each subsystem. For example, you see in this figure that the waterway can be divided into three parts: the part around the guide vanes, the distributor, the rotor, and the draft tube. And then within each subsystem, you have quantities of different types. Clearly, mainly fluid dynamic for the distributor or the draft tube, but then the rotor has also quantities that are related to fluid dynamics, but also mechanical quantities like stresses, torque. And also the rotor has interface, a structural interface with the shaft, and the shaft has a structural interface with the generator, while the generator has both mechanical and electric quantities in its, involved in its operation. And then you also have the control systems to change the position of the guide vanes or the blade angles in the rotor. All these subsystems involve some relationship that can be described with neural networks. Of course, this decomposition and the training of the neural networks within each subsystem is possible as long as there are enough sensors placed in the turbine, in particular at the boundaries of these subsystems. So you can see in the figure that the waterway can be divided in three subsystem, and then you have to place some intermediate pressure sensor before and after the rotor in order to have the pressure drop versus flow characteristic for each of the three subsystems. And if this decomposition is performed properly, then each performance degradation or fault can be identified in a sort of table of truth, where the differences of between the predicted quantities and measured quantities point to a specific performance degradation or faults, because the effects are different if you measure them in these table of truth. Then these patterns that are specific to each performance degradation or faults can be implemented as rules in an expert system. So this expert system triggers the, let's say, alarm or warnings that something is going wrong, knowing exactly what is going wrong. And of course, this expert system can take advantage of fuzzy logic to allow for a band of uncertainty due to the measurement uncertainty. So what is the ultimate goal of this exploitation of the results with the neural networks? Well, the information from about from the expert system about the performance degradation and the faults allow the managers to estimate more precisely the cost for running the turbine in the current operating conditions. Because if there is a performance degradation, you know the cost of it. Or you can also monitor with the data acquisition system the vibrations to some mechanical components, and then you can estimate the life expectancy for those components. So the ultimate goal is to optimize the profit of running the turbine under given operating conditions, and not only the revenue. So the profit, of course, is the difference between revenue and costs. And the neural network results allow you to have a more precise idea of running costs. So the conclusions, the project results show a good accuracy for the neural network models. Of course, we didn't check only the turbine efficiency, but also other quantities that would belong to show here. The neural network models are important because they are computationally simple and can be used, for example, for diagnostic applications. And then finally, the information from the diagnostic expert system is useful for cost estimation and allows the optimization of the turbine operation profit. Finally, I would like to acknowledge the Swedish Hydropower Center and the other co-funding partners for this project, which are Vattenfall, Skellefteå and our university, Luleå University of Technology. Thank you for your attention.
Thank you, Andrea. Very interesting. Now I welcome Mattias Nesselqvist into the discussion. I will let you introduce yourself, Mattias, and then I'm very excited to hear your thoughts about these two projects.
Yes, thank you for very good presentations. As Andrea mentioned, my name is Mattias Nesselqvist. I work at Vattenfall R&D and has been here for a pretty long time and worked with hydro. And I also was a researcher within SVC, but within router dynamics. So I'm not a specialist within machine learning. But I think the first I have a question to Xiao. What is required to use this model on a real hydropower station instead of the turbine test facility?
Yes, thanks.
For example, if you wanted to optimize startup times and to be able to predict the startup times, since it can be depending on how the head varies and things like that.
Yes, I guess the input to future is how to make this model is different. Since in the task rig we have pumps, and also we can decide how we want to, how the height variation we want to achieve. Is minimize fluctuation we want to have a different shape of the height change. But in the real hydropower plants, I think the methods can be used. But the input features, how to make the height prediction model, is depends on how many sensors, how many parameters we have, and also how their future importance to the real height in the real hydropower plants. So the method is okay. So we should test the real data with the methods and check the accuracy, and also check the generalization capability of the models. And if the model is okay, and then we can combine with the controller to see if we can control the height in the real hydropower plants based on our plan. But still, I have think, since in the task rig, is a really high frequency, so the quasi-static model is not work. Actually, for the height recovery or the pressure recovery, but for the real hydropower plants, maybe the quasi-static model can be used, since the time is not the time, the frequency will not be so high. I mean the height change. Yeah.
And I guess like for most of this type of models, you need to have also the whole range of the operating conditions for the machine with high head, low head, and you need to have the right sensor and with high quality.
For sure, this is the best condition.
Is it easy to identify in advance which sensor do you need to install? What information do you need before if you are asked to, for example, optimizing the start time? Do you know? Yeah.
Yes. Also, this is an interesting question. Since my background is not in hydropower, so I graduated with PhD in shipping. So I have some experience in shipping. So first, actually, we have 3-stage method. This is the physics-based model. So we know how the different parameters influenced by others. So this is, we can use the physics to find the relationship between different important input features. And the second, we use the physical understanding to extract the variable sensors data to construct the model. The second stage is the black box model, machine learning model. Okay, so we can use physics to get the data we want. And also, if we have a lot of data, we can use the machine learning to identify which parameters has the highest importance. And also I have another question, another answer to your previous questions, is that if we do not have so many data, how can we achieve a good data-driven model? So we have the third stage model is we combine the physics and the machine learning as a gray box. So we use the physics to constrain our models, but we use the machine learning method to actually interpolate the results. So, and also in this case, since the hydropower plants is continued operation, right? So the new data come, we can update our data. So this is now a static data. So the model can be updated based on the data stream day by day. So the model will be better and better. Yeah.
Okay. Well, thank you. I jump over to Andrea with the question. You said that you make a fingerprint when the machine is in a good state, and then you try to identify, get it more detailed down to subsystems regarding what is deviating. Do you have to train it with those errors?
Yes and no. You can simulate the errors. For example, you know that if you have an obstruction in a waterway, or let's make it easier, in a pipe, your pressure drop flow characteristic will change, but you know how it will change, right? So these are the simpler example. However, for the structural parts, you have to make some sort of let's say experiment on smaller models. This idea that I presented was actually developed into a proposal for the EU Horizon call. Unfortunately, it was not granted, but our partners at the University of Barcelona had in mind to test these, for example, a crack running in a shaft, and see what are the consequences, so that the network could be trained according to these consequences, and then the fingerprints compared between the healthy state and the non-functioning state. So yeah, in a sense, you have to train, but you also have to simulate the fault first.
Yes, I think a challenge within Hydro is that all machines are individuals, so they have like a different behavior.
No, clearly, all networks must be trained specifically for one plant.
And also, fortunately, we have the frequency of faults isn't that high, but it's since we have old machines, so it's a not different type of faults that occurs, and it's not that easy to simulate those faults, maybe. And I think one challenge is also I assume you want to have good flow measurements, for example, if you need to know the deviation in the turbine. And
Yes.
I guess that today we don't have good enough accuracy for the flow measurement, I guess. But I know that LTU are also looking on developing.
Yeah, Michelle is doing a lot of in that respect. But you can always take into account, let's say, a band of uncertainty if you implement these rules with fuzzy logic. So it is possible to take into account and see. I mean, it's not really an on-off answer. So you have a certain degree of confidence that something is going wrong.
Yeah, good. I think that if I just summarize my understandings of both of your presentation is that you have tried to identify what are the best models depending on what you want to be able to predict, and I think that is very useful. Then it's always a very big challenge to implement it in the reality, and it's especially maybe in our application where it depends on which season it's and which head we have and which generation of hydropower unit it is. So it's it's good. We need to be able to work smarter, but it's not very simple, I think.
Thank you for participating.
Thank you.
Thank you.
Thank you. Bye.